Welcome to the second lecture on wireless communication. In last lecture, we discussed about the overview of modulation schemes, why we prefer digital modulation for wireless communication, and we came to the conclusion that there are two important efficiency measures. One is power efficiency, and the other is bandwidth efficiency. Okay. Now, power efficiency is sort of a measure of how favorably we can have a trade-off between fidelity and signal power. What is fidelity? It is an acceptable bit error rate. See, you would like to have a minimum performance in terms of bit error rate. You would like to have less error in one way. Okay, and at the same time, you want your signal power to be not so high. So power efficiency, which is expressed as a ratio of energy bit to the noise power spectral density. You might have done power spectral density in your random process course. So if you treat noise as a random process and you find its autocorrelation function, then the Fourier transform of autocorrelation function of noise is power spectral density. Those of you who don't understand it, just take n naught as some measure of noise power. Okay, if you take noise as some random signal, n naught is the average measure of power of noise. So ratio of the energy per bit, which is actually related to the energy of signal, to the noise power ratio, is power efficiency. So we would like to have a particular power efficiency value at receiver, but we would also like that power efficiency to satisfy some minimum bit error rate constraint. I would not like to have more errors. Suppose I want 10 to the power minus 5 probability of error. It means out of 1 lakh bits there is just one bit in error. Okay, so you will see that the modulation scheme has impact, that which digital modulation scheme you will adopt. It has very great impact on the choice of power efficiency. The other important factor is bandwidth efficiency, which is the ability of any modulation scheme to accommodate within the limited available bandwidth. See, we know that to increase the data rate, we need to decrease pulse width, right? Suppose you have a pulse width of 1 millisecond. If you want to increase the data rate, just make it 1 microsecond, right? So you can adopt 1,000 more pulses in the same width. But if you decrease the pulse width, the bandwidth will get increased, right? So you all are aware of, you know you have done this. So if you have a pulse is usually a rectangular signal, right? And its Fourier transform is denoted by sync, right? And if you decrease the pulse width, okay, suppose you make it like this, then the sync function, its amplitude will increase. You will observe that its amplitude will increase, so hence more bandwidth. Although we are going to define bandwidth very soon, we will see at that time what it means. So there is a trade-off in rate and bandwidth. So you want to increase rate, so you would like to decrease pulse width, but there is increase in bandwidth. Now the ratio of rate and bandwidth is called bandwidth efficiency, measured in bits per hertz. R is the data rate measured in bits per second. B is the bandwidth occupied by the radio frequency signal. So you want this you want this bandwidth efficiency to be as high as possible, right? If you see it is a ratio of R and B, so to make it as high as possible, you want to increase R, you want to decrease B. Okay, but there is a trade-off. So the question is, can we connect them? Can we relate power efficiency, bandwidth efficiency? And yes, the answer is yes. It's already related by a famous Shannon's channel coding theorem. It says that for small probability of error, suppose you are transmitting a digital sequence of bits, binary bits, and you want very small probability of error. Then it says the maximum bandwidth, possible bandwidth efficiency, that is the ratio of maximum rate by bandwidth, is limited by noise in the channel. Okay, so noise becomes a bottleneck here. So it means you cannot go on increasing rate. You cannot go on increasing rate and decreasing bandwidth, and achieve any infinite or very high value of bandwidth efficiency. There is upper limit that is given by log of 1 plus s by n. Okay, s by n is signal to noise ratio, SNR. Channel capacity, which is the maximum data rate which we can achieve, its bits per second. We see a clear trade-off. We want less bandwidth, less SNR, but more efficiency. You see, there's a trade-off. You cannot achieve everything. We'll come to this point again when we will shed some more light on the channel capacity. So these are not the only factors. There are other factors also which are important in making the decision of which modulation scheme you should use for wireless communication. Suppose cost and complexity of receiver. Receiver means mobile. In 5G jargon, we call mobile as user equipment, UE. We also want the performance of wireless. You want performance of digital modulation schemes to be very nice under wireless effects, attenuation, multipath fading, shadowing. We are going to study it in very detail, separate topic for it. We also want that it should perform very nicely in presence of interference. Okay, when we will go for cellular communication, you will see there's interference, right? You are hundreds of mobile users are communicating to the same base station. Definitely there is interference. And of course, modulation scheme should perform better over the channel, which varies with time. Wireless channel changes with time. Things are moving here and there. It's a very dynamic channel. Now, I would now like to define the bandwidth and power spectral, density of digital signals. So, but that and for that I will be posting one more video, and we will have a detailed discussion on how to define it. Okay, so hold on, and I will share one more video with you people. Thanks.